What happened in New Orleans in August 2005 wasn't a natural disaster. Don't get me wrong, Hurricane Katrina was a big storm. By many measures, it was one of the strongest hurricanes to ever crash into a United States coastline. It's in the top 10 for largest diameter, lowest central pressure, highest integrated kinetic energy, and more. Storm surge along parts of the Gulf Coast crested at nearly 28 feet or 8.5 meters, the highest in U.S. history. There really are no words to describe the devastation Katrina caused, particularly in New Orleans and the surrounding areas. Roughly 4/5 of the city was flooded. In some areas, the water rose above the roof lines of houses. The storm shredded the fabric of the city, and to this day, more than 20 years later, the population of New Orleans has not recovered to its pre-Katrina level. If this were just a story about a major storm overwhelming the flood defenses, it wouldn't undercut the tragedy, but it would be understandable. I think we generally recognize that these kind of systems don't offer absolute protection. The levees and flood walls around New Orleans were a sprawling collection of structures built over many decades. It wouldn't be out of the question for a storm of the century to simply exceed what those protections were designed to handle, but that's not what happened. There were about 50 individual locations where levees or flood walls were breached during Hurricane Katrina. Many of those were situations where the structure was overtopped by storm surge. But out of those 50, only 3 of those breaches accounted for the majority of the flows that submerged the heart of New Orleans and led to nearly half of the disaster's total fatalities and economic damage. All 3 of those breaches happened at surge levels below what the floodwalls were designed to manage. And I built a model in the garage to show you why. This video is based on a chapter from my new book, Disasters by Design, which you can pre-order right now at the links below. The book is all about engineering disasters through history and what we learn from them, and I really hope you'll consider picking up a copy. I'll tell you more about it at the end, but first I want to show you this model. I'm Grady, and this is Practical Engineering. The land we call New Orleans has a history stretching way beyond its 1718 founding or the birth of the United States. Originally inhabited by tribes like the Chitimacha, this area has always been a complex intersection of human settlement and flooding. It is strategically located on the Gulf Coast at the mouth of the Mississippi, the largest river in North America. But that prime location also comes with challenges, namely that the city's exposure to tropical storms is extreme, and being a river delta, much of its development happened on top of historically soft, marshy, and low-lying terrain. In 1965, Hurricane Betsy rocked New Orleans, flooding more than 150,000 houses. At the time, it was one of the worst hurricanes in American history, earning the nickname Billion Dollar Betsy because it was the first storm with damages in excess of $1 billion. In response, the federal government, through the U.S. Army Corps of Engineers, made a massive investment into the existing hurricane protection system around New Orleans, but they ran into an issue. A levee is an earthen embankment meant to hold floodwaters back. Kind of like a dam, but parallel to coastline or river instead of across it. We know that soil is naturally unstable on steep slopes, so levees have this trapezoidal shape in cross-section, with gentle, stable slopes on the water side and land side. Many of the levees in New Orleans were built decades before Betsy, and over that time, development encroached right up to the toes of the structures. You can see the problem. If you want to raise the embankment to provide more protection, you need more space. The solution they came up with is the eye wall, not related to the eye wall of a hurricane. Steel sheet piles were driven into the top of the levee, creating a vertical flood wall on top. They got more height and more protection without the need to condemn property for a wider footprint, which was a major win. All this flood protection infrastructure turned New Orleans into essentially a bowl. The levees keep the floodwaters out, but they also trap rainwater or any other water in. So in addition to the levees and floodwalls, the city is dotted with pump stations that move drainage within the city out of the bowl. The heart of the system is the trio of primary outfall canals that run south to north, carrying rainwater from New Orleans' interior basins out to Lake Pontchartrain, the 17th Street Canal, the Orleans Avenue Canal, and the London Avenue Canal. Where most canals, rivers, and creeks in cities represent a topographic low point, these canals are somewhat of a high point in New Orleans. Runoff within the city naturally flows in street gutters and underground storm drains, eventually reaching one of the massive pumping stations associated with each canal. Those stations raise the water just a little bit higher than Lake Pontchartrain, and then gravity takes care of the rest, with the water flowing northward out of the city and into the lake. The problem is that Lake Pontchartrain isn't really a lake. It's an estuary with a direct hydraulic connection to the Gulf of Mexico. It functions as an arm of the sea, which means it's subject to the same tidal forces and catastrophic storm surges as the open ocean. When Hurricane Katrina pushed up a wall of water, the outfall canals stopped acting like drainage ditches and turned into conduits, penetrating deep into the heart of New Orleans, inviting the weight and pressure of the sea miles inland. You can see why the breaches along these levees were particularly serious. In the morning on August 29th, just after landfall as storm surge began to peak, 3 failures along the outfall canals happened in quick succession. Maybe the most well-known was the breach on the 17th Street Canal levee and eye wall. That morning, water was several feet below the top of the wall. This structure should have been more than capable of holding back the surge, but a huge chunk of the levee shifted, leaving a 450-foot or 140-meter wide gap for a torrent of storm surge to flood the Lakeview neighborhood and surrounding areas. It's a little tricky to understand how something like this could happen, so I built a model of a levee and eye wall in my garage to show you how this works. This is just a narrow tank that I built out of sheets of acrylic. On the left side, I have a pump that will move water into the system. This area represents the canal side where storm surge flowed in from Lake Pontchartrain. I have an overflow that will keep the water level constant. I don't know how well this shows up, but the soil that I'm using for the levee and its foundation is a blend of ground up plastic and sand. And then on the right side, I have a drain that kind of represents the pump stations that move surface water out of protected areas to keep them dry. This took a few tries to get to work right. I'm sure anybody who's built a garage storm surge simulation can relate. First, the colored liquid dyes weren't persistent enough. Then my eye wall sprang a leak. So I've got solid dye tablets in the soil and the leak hopefully fixed. And you can see that there's not much happening when the water level in the canal is low. But watch what happens when I turn on the pump. The levee and eye wall hold the water from the canal back, keeping the homes and businesses on the land side protected. But keep an eye on the dye in the soil. I'll speed this up a bit to make it clearer. Water is still making its way toward the land side of the levee, not above ground, but in the subsurface. It might seem obvious that this would happen, but it's not a phenomenon we get to see with our eyes very often, and it makes one thing about flood protection systems abundantly clear. These levees aren't just piles of dirt. They are engineered structures that have to consider some fairly unusual and unintuitive loading conditions. And the behavior of this subsurface flow is absolutely critical to their performance. It's easy to follow the flow in the model, but it's harder to visualize the water pressure, so I coded this little companion toy simulator to go with my model. Thanks to Dan Schiffman at the Coding Train for teaching me JavaScript and P5. It takes a minute to converge on a solution, but when it does, it plots the pressure contours in the subsurface. Differences in pressure are what drive flow, so these contour lines are perpendicular to the flow lines you see in my model. And I gave the pressure a color gradient to make this more clear. You can see that even though it's not as high as the areas closer to the canal, there's still water pressure in the subsurface on the protected side of the levee, and that's a problem for a structure trying to hold back an immense wall of storm surge. Soil grains work kind of like a pile of marbles. Squeeze them and they lock together, increasing their strength against shear. You can imagine if you were able to inject water between those marbles, it would push them away from each other. As a mass altogether, they would be a lot less strong, and it works the same way for soil. Engineers have to take this into account. The calculations when designing a levee aren't just about how hard the water pushes against the structure, but also how hard it pushes inside the foundation. If the soil doesn't have enough strength to resist the force of the water pushing sideways, while the subsurface water pressure is also pushing the soil particles away from each other, it shears along the plane of weakness. That's exactly what happened at the 17th Street Canal. The thing is, it happened at a lower water level than anybody expected, and here's why. It is no small task to assess the complex subsurface conditions along miles of levees and floodwalls. During the improvements made in the wake of Hurricane Betsy, geotechnical engineers drilled hundreds of boreholes, collected samples, and tested their strengths in labs. Here's a look at that data plotted as a function of depth. Now, when you're designing miles and miles of levee, it's not feasible to analyze every single inch. Instead, you pick representative sections, and you really want those sections to be the worst ones. That's just efficient engineering. You know that if a design works in the weakest spots, it will work everywhere. But for some reason, that's not what was done. Knowing that kind of fundamental principle and looking at this data, what would you choose as your representative soil strength for design? If it were me, I might choose something like this, assuming a few of the test values are outliers that don't represent the bulk properties, but for the most part, being conservative by assuming strengths at or below what was measured in the field. For some reason, the Corps of Engineers drew their line here, assuming the soil was stronger than a majority of the measurements. And what's worse is that those measurements were taken along the center line of the existing levees, where the weight of those structures had artificially consolidated and strengthened the soil. Outside of that center line, the soil was actually much weaker. These decisions led to the levee failing at water levels lower than the structure was designed to handle. What made things even worse was a critical flaw of the eye wall idea. It seemed elegant on paper, an efficient way to get more height out of a levee without widening its footprint. But when they were actually put to a true test during Katrina, those walls bowed out, opening a narrow gap deep into the levee's foundation. Let's look back at the simulator to see the difference in pressure. You can see that with the so-called water-filled gap, you get more pressure in the foundation of the levee. This also shortens the length of soil shear needed to cause the levee to fail. All these factors resulted in the levee on the 17th Street Canal failing at a level below what it was designed to withstand. The same thing happened nearby on the north side of the London Avenue Canal, and actually that failure was exclusively the result of the flaw in the eye wall design. If the wall wouldn't have deflected to open the gap, the failure wouldn't have happened at all. But that wasn't the only failure that happened on the London Avenue Canal, and the one on the south side was even more egregious. This levee was largely the same as the one on the 17th Street Canal with the embankment and eye wall, and it had the same situation with water seeping through the foundation below. But there was one critical difference. The levee rested on a thin layer of marshy clay above a thick bed of permeable sand. Again, it's hard to show pressure in the garage model, so let's take a look at the simulation. You can see when I use a homogeneous material for the soil of the levee and foundation, you get fairly nice, even spacing of the pressure contours. Let me make a change to add a layer of less permeable material like the London Avenue Canal South and run them side by side. With the marsh layer, you get a really different result. The pressure contours stack up right where the water comes out on the protected side. Geotechnical engineers would say there's a steep exit gradient, and here's why that matters. Let's take a block of soil and look at it more closely. Because of the steep gradient, the pressure at the bottom of this block is different from the pressure at the top. That difference in pressure means there is a net force pushing it upward. If that net force exceeds the weight of the block itself, it's going to move. And I can show it in my demonstration even without the marsh layer. I've reset the demo, but I added an extension to my overflow so the water level will be higher on the canal side now. Even though the pressure gradient through the subsurface is evenly spaced since I'm using a homogeneous material, unlike the layers in New Orleans, it's still steeper just because there's a bigger difference between the water levels on either side. And because I'm using a lightweight plastic blended into the soil, the so-called critical exit gradient is much lower than it would be for a denser sand. And it's easy to see that we've exceeded that critical gradient. The particles are dislodging as the seepage comes out of the ground on the protected side. The erosion just keeps getting worse until the levee on the protected side fails. Eventually, the eye wall loses support and you get a total failure. This is exactly what happened at the London Avenue Canal South. As the storm surge rose, water seeped through the sand, building upward pressure on that marsh layer. Eventually, the pressure got high enough that it literally blew a hole through it. With the sudden release of all that built-up pressure, the subsurface water was able to erode a mountain of sand from the foundation. There are pictures of this, a neighborhood covered in what's basically beach sand. All that erosion caused the eye wall to collapse, opening a wider hole in the levee and letting the full force of Lake Pontchartrain through. This was not some unknown issue. The Army Corps of Engineers analyzed the seepage forces through the levee when they built the eye walls, but inexplicably they left that marsh layer out of the calculations. One of the investigation reports said it clearly. If a more rigorous analysis had been performed at the time of design, the potential problem would have been predicted and corrective action taken. Those 3 breaches created a majority of the problems in the center of New Orleans, but there were a lot of levee and flood walls that overtopped in the surrounding area during Hurricane Katrina. One of the worst cases was at the Industrial Canal, where the wall was lower than intended because of ground subsidence and confusion about elevation benchmarks. In that case, the water spilling over the top of the wall eroded the soil, causing the levee and wall to fail. And that gets to the heart of a very complicated problem with flood protection. You can't build a 100-foot-tall invincible wall around the city. You have to draw a line somewhere below absolute safety to a level that's economically feasible. That means there are going to be potential storms that overwhelm the system, which makes designing levees even more complicated. Let's make a graph of depth versus damage. In an area with no flood protection, you might get a curve like this. Just a little damage at first when depths are low, and those damages increase as flood depth grows. If you build a levee, of course, you basically eliminate those damages below the protected level. And above the level, the curve stays the same. Once the levee overtops, even the protected areas flood, so there's no change there. But over time, a funny thing happens. Before the levee was installed, the lowest places weren't heavily developed because flooding happened there regularly, and people generally knew and understood the risk. But once those low areas are protected, and some time with no flooding at all passes, people build stuff in them, homes, businesses, etc. We put a lot of valuable stuff on that previously mostly empty land. So where the depth damage curve with the levee started like this, now it looks like this. Just a tiny bit of overtopping means an enormous amount of damage because the former floodplains have all been built out. So if you look out toward the long term, the damages you can expect from flooding over many decades is actually much more than would have happened if the levees were never built. This concept is sometimes known as hazard creep, and it's the thing that no one recognized in New Orleans. The shadow of the flood protection system had, in some ways, only made things worse. In that way, not only did the engineering, particularly along the outfall canals, fail to protect the city, the Corps of Engineers estimated that roughly 2/3 of the deaths during Katrina would not have occurred had the levees and flood walls not failed. They generally created a situation where the damage and loss of life was much worse than it would have been in an unprotected area. Of course, that is really just one tiny piece of the story of Hurricane Katrina. The investigations that followed filled volumes and volumes, tens of thousands of pages, just on the engineering issues alone. When you add in the challenges and controversies associated with the evacuation, rescue operations, and recovery efforts, you could spend your entire life trying to wrap your head around this one event. I know because I spent a good chunk of my life researching it while I was writing my new book, Disasters by Design. I think there's a lot we can learn from past mistakes, and I really hope you'll click on the link below or head to your local bookstore and pre-order a copy. That's the thing about engineering disasters. When they first happen, journalists scramble to tell the story with whatever information they can find. Politicians and pundits offer premature reactions, and then slowly public interest wanes. By the time rigorous investigations are carried out and a consensus has formed around what really happened, most people have already moved on. So in lots of cases, the documentation of an engineering disaster is this rigorous and complex forensic report produced months or years after the fact that a handful of experts read and not much else. Here's the problem with that. For better or worse, a great deal of humanity's most important lessons in engineering have been learned the hard way. Humans are capable of, and maybe even prone to, making stupendous errors in judgment, calculation, and prognostication. The only way we've reached this era of remarkable advancement and connectivity is through learning from those errors and striving to avoid repeating them. All the people who studied, investigated, and documented the engineering failures of history did so because they wanted, in some way, to help prevent us from making the same mistakes again, but they often wrote to an audience of other engineers, meaning many of humanity's most important lessons are tough to wrap your head around unless you have the context, background, resources, and education to parse and understand those sometimes impenetrable reports. I wrote this book because I wanted to bridge that gap. I've spent a career working on infrastructure projects as a civil engineer, and another career breaking down engineering concepts to people like you on YouTube. I wanted to combine those experiences and curate a collection of stories throughout history that I've found to be most enlightening. But these aren't just stories about disaster and tragedy, they're also stories about what we learned as a result and how we transform tragedy into hope. Because some of the most important aspects of the built environment and the industry that surrounds it came as a result of something terrible. In that way, the stories of engineering failures are the stories of engineering itself and how it's evolved over time. New Orleans is a perfect example. The city's flood protection system looks a lot different than before Katrina. There are huge gates on the canals to keep Pontchartrain from backflowing into the city. Levees have been raised and strengthened, the flawed eye walls were taken out, there's a huge new storm surge barrier in Lake Bourne. But it wasn't just steel and concrete structures that resulted from the storm. The Corps of Engineers completely rewrote the manual for levee engineering. Incorporating the lessons learned, they did a nationwide review of existing eye wall projects. The federal government implemented the National Levee Safety Program to support owners and enhance public awareness. Lots of those lessons were incorporated into the International Levee Handbook that's used around the world. It changed so much in engineering, disaster response, and even government. It's tricky to see how all this plays out because it really just means quiet. There won't be any news stories that some levee didn't fail today, and that's why I wrote the book. To really get a sense of how the field of engineering has evolved over time, from antiquity to today, you have to look at the disasters that precipitated the big changes. And I really think having those major events laid out in order and explained so curious people can understand them with lots of illustrations is the right way to comprehend engineering history. So yeah, the book will be published in March of next year. I'm super excited about it and really proud of how it came out. I know that's a long time from now, but pre-orders are really important with books because they have to know how many to print. I know I ask you to click a link at the end of all my videos to support the channel via our sponsors, but this time it means so much more. Grab a first edition for yourself, and if you have friends, professors, a significant other, or family members who are interested in engineering, it would make a great gift. Your support and encouragement has made this book possible, and I'm so grateful to have you along for the ride. Thank you for watching, and let me know what you think.